So in the previous lessons, we've looked at several ways in solving differential equations, and in this video or in this lesson, we are going to look at linear first order differential equations. So a linear first order differential equation is a differential equation which is given in the form dy dx plus p of x times y equals q of x, where p and then q are all functions of x. So given any linear first order differential equation, the first thing we need to do is to represent the differential equation given in this form, that is in the form dy dx plus p of x times y equals q of x. And then we write down the expressions for p of x and then q of x. So that is the first thing we need to do. Now, secondly, we are going to recognize the differential equation given as a non-exact differential equation. Now, you remember that when we were dealing with non-exact differential equations, we looked at, or we found out, what we call the integrating factor, and then we multiply the differential equation by the integrating factor. So in this case, we are also going to find the integrating factor, and the integrating factor if, which is a function of x, is given as e to the power the integral of the function p of x dx. Now, after finding the integrating factor, the next thing we are going to do is to solve for the general solution. So you solve for the general solution. Now, this happens to be our first example. That is where we are going to solve the initial value problem, dy dx plus 3y over x equals x squared. And then we have an initial condition, y of 1 equals 1 over 6. So let's try to solve our first example. So we have the differential equation dy dx plus 3y over x equals x squared. Now, this differential equation is already in the form we are looking out for. Okay, we have dy dx plus 3y over x equals x squared. So what we need to do is to write down the expression for p of x and then q of x. So we have p of x to be equal to 3 over x, and then we have q of x also to be x squared. Now, the next thing we are going to do is to determine the integrating factor. So the integrating factor, which is a function of x, is equal to, we have e to the power the integral of p of x dx. Now, this is equal to, we have e to the power the integral of p of x is 3 over x. So 3 over x dx. And this is equal to, we have e. Now, because 3 is a constant, we are going to pull out the constants, and then we have the integral of 1 over x dx. Now, let's try to integrate 1 over x. So that becomes ln of x, and then we can represent this as e to the power ln of x cube. Okay, and then from properties we know that e to the power ln of x is equal to x. Now, in that case, e to the power ln of x cube is equal to x cube. Therefore, we have the integrating factor, that is mu of x, to be equal to x cube. So this is the integrating factor, mu of x. So after finding the integrating factor, the next thing we are going to do is to solve for the general solution. We are going to solve for the general solution. So that is given by y equals 1 over mu of x times the integral of mu of x times q of x all dx plus c. So let's put in the expressions mu of x and then q of x. So that's going to be 1 over, now in place of mu of x we have x cube. So x cube times the integral of x cubed times k of x is x squared, so x squared or dx plus c. Next we have 1 over x cubed times the integral of x to the power, so we have x to the power 3 plus 2, which is x to the power 5 dx plus c. So we have 1 over x cubed times, now when we integrate this, we increase the exponent by 1, we divide by the total exponent, and then we are going to multiply 1 over x cubed across, so that becomes x to the power 6 divided by 6x cubed plus c over x cubed. So we simplify this as this cancels out 3x's here, and then we are left with 3, so that is x cubed over 6 plus c over x cubed. So this is the general solution to the differential equation. The general solution to the differential equation. Now, we were given an initial condition of y of 1 equals 1 over 6. So let's try to find the particular solution. So we had the general solution, that is y equals x cubed over 6 plus c over x cubed, and then we have initial condition y of 1 equals 1 over 6. So this primarily means that x is equal to 1 and then y is equal to 1 over 6. So let's plug in the values of x and y in here. So for y we have 1 over 6 equals, we have 1 cube over 6 plus c over 1 cube. So this becomes 1 over 6 equals 1 over 6 plus c. We transpose this to the left hand side, it becomes 1 over 6 minus 1 over 6, which is 0, equals c. Therefore we have c equals 0. So this is the value of c. Now let's plug in the value of c back into the general solution to obtain the particular solution. That is y equals x cubed over 6 plus 0 over x cubed. Now 0 over any non-zero number is 0, so we have the particular solution to be x cubed over 6. So y equals x cubed over 6. This is the particular solution for the differential equation given the initial condition y of 1 equals 1 over 6. So basically this is how to solve a linear first order differential equation. Now let's move on as we solve the next example. So for example 2, we have the differential equation x times dy dx minus y equals x squared cos x, and we have an initial condition y of pi on 2 equals pi, and then we are asked to solve the given differential equation. So we have the differential equation, that is x times dy dx minus y equals x squared cos x. Now let's try to represent this differential equation in the form dy dx plus p of x times y equals q of x. So we are going to divide through by x. So let's say we have x over x dy dx minus y over x equals x squared over x times cos x. So this cancels out this also cancels one of it, and so we are left with dy dx minus y over x equals x times cos x. So this is in the form we are looking out for. So let's write down the expressions for p and q. So we are going to have p of x to be equal to negative 1 over x, and then we have q of x to be equal to x cos x, x cos x. So next, let's find the integrating factor, which is a function of x and is equal to e to the power the integral of p of x dx, and that is equal to e to the power the integral of, we have p of x to be negative 1 over x times dx. This is equal to, we are going to pull out negative 1, and then we have the integral of 1 over x dx. So the integral of 1 over x dx becomes ln of x, and then we can further represent this as e to the power ln of x exponent negative 1, which is finally e to the power ln of 1 over x. Now, since e to the power ln of x is equal to x, then e to the power ln of 1 over x is equal to 1 over x. So that is mu of x, the integrating factor. So we have the integrating factor mu of x to be equal to 1 over x. Now let's move on to find the general solution to this differential equation. So the general solution, as usual, is given by y equals 1 over mu of x times the integral of mu of x times k of x or dx plus c. So we have y equals 1 over x. So 1 over x, and then this becomes 1 times x over 1, which is equal to x. So we are going to have y equals x. We are going to have y equals x times the integral of mu of x is 1 over x times q of x is x cos x. So all dx plus c. So this becomes x multiplying, this cancels out this, we have the integral of cos x dx plus c, and this is equal to x times. Now if you integrate cos x with respect to x, then you have sin x. So we have sin x plus c. Therefore we have the general solution, y to be equal to x times into bracket sin x plus c. So this is the general solution to the differential equation. Now we have the initial condition, y of pi on 2 equals pi. So it means that y is equal to pi, x is equal to pi on 2. So we have y to be pi equals pi on 2 times sine pi on 2 and then plus c. So we are going to multiply both sides of the equation by 2 to do away with this fraction. So we cancel out 2 and then 2. We are left with 2 pi equals the right hand side. We can cancel out pi and then pi, so that we have 2 equals sine pi on 2 plus c. So the value left here is 1. So 1 times everything here is still the same thing. Now sine pi on 2 is the same as sine 90, and then sine 90 is equal to 1. So we are going to have 2 equals 1 plus c, and then we transpose 1 to the left hand side. We have 2 minus 1, and that is equal to c. Therefore we have c to be equal to 1. So the value of c is equal to 1. So we are going to put in 1 in place of c in this general solution. Okay, so that's going to be y equals x into bracket sine x plus 1, and this happens to be the particular solution of the given differential equation given that y of pi on 2 is equal to pi. Now let's move on to the third example. So in the third example, we are also going to solve the differential equation dy dx equals sec x plus y tan x, given the initial condition y of 0 equals 1. So let's solve this together. So we have the differential equation given in the form dy dx equals sec x plus y tan x. Now this is not the form we are looking out for, so we can transpose y tan x to the left hand side. So that becomes dy dx minus y tan x equals sec x. So we can say that p of x is equal to negative tan x, and then we have q of x also to be equal to sec x. Now let's find the integrating factor. So we have mu of x equals e to the power the integral of p of x dx, that is equal to e to the power the integral of p of x is negative tan x dx equals, we have e to the power, so we have this to be negative 1 times tan x, so we can pull out the negative, and then we have integral of tan x dx. Now when you integrate tan x with respect to x, then you have ln of absolute value of sec x. So that's it, and then this becomes e to the power ln of sec x to the power negative 1. Now sec x is equal to 1 over cos x. So what this primarily means is that sec x to the power negative 1 becomes cos x over 1, or better still, cos x. So in place of sec x to the power negative 1, we are going to have e to the power ln of cos x. Now since e to the power ln of x is equal to x, then e to the power ln of cos x is equal to cos x. Therefore we have mu of x to be equal to cos x. So let's find the general solution. So we have y equals 1 over mu of x times the integral of mu of x times q of x or dx plus c. So y equals 1 over cos x times the integral of cos x times q of x, and q of x is sec x. Now sec x is 1 over cos x, that is 1 over cos x, so we are going to have 1 over cos x or dx plus c. So cos x cancels out cos x, we are left with y equals 1 over cos x times the integral of 1 dx plus c. So that becomes y equals 1 over cos x times, when you integrate 1 with respect to x, you have x, and then plus c. So we say that the general solution is given by y equals sec x into bracket x plus c. This is the general solution. Now for the initial condition given, y of 0 equals 1, y equals 1, x equals 0. So we are going to plug in the values here. So we have 1 equals, now this is sec x. We are going to move one step backwards, and then we have 1 over cos x. So that is 1 over cos 0 all times 0 plus c. So we have 1 equals, now cos 0 is 1. Okay, so cos 0 is 1. So we have 0 plus c is still c. Therefore, this becomes 1 equals c. So we have the constant c to be 1. Therefore, coming back to the general solution, we have y equals sec x into bracket x plus 1. So this happens to be the particular solution of the differential equation, given that the initial condition y of 0 is equal to 1. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.